Alright, yes. Let's take a look at this example here. We'll read it through. We just barely introduced this yesterday, right? Did we introduce it at all, or?
No,
we did not.
Okay.
I think we were back.
That's fine. Either way, I'm going to start from the beginning here, because it says an airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees at a fixed altitude with negligible wind velocity. That whole part is just eliminating variables, okay? As the airplane reaches a certain point, it encounters a wind blowing with a velocity of 70 miles an hour in the direction of north 45 degrees east, as shown here in figure B. What are the resultant speed and direction of the airplane? Now let's look at some key parts here and explain a little bit of what's going on, okay?
I thought figure B, I thought east was this way, like never eat.
Yes, east is this way.
So why is it like that?
Well, we'll explain, okay? Let's just look at this one step at a time. First of all, it said that the airplane is traveling at 500 miles per hour with a bearing of 330 degrees. And the one question is, why do they have 120 degrees when it's 330 degrees? And that's because this says it's a bearing of 330 degrees. How do we measure bearings?
Clockwise.
Clockwise from? North. So starting here, we rotate clockwise 330 degrees. And this is what we were mentioning yesterday, where if you're given angles in different forms, you need to translate it to the direction angle. Okay? For the vector, the direction angle is what we're going to use to find the component vectors, remember? So, in order to do that, we have to look at this and we say, okay, if that's 330, then this little piece up here is 30. Because that would make a full 360, right?
Yes.
So now, our direction angle is always an angle from the positive x-axis, or due east, counterclockwise. Well, that's 90 plus 30, 120 degrees. Okay? So that's how they get the 120 when we were given 330. Okay? That's important because, as we saw yesterday, when you're finding your unit vector for the direction you want to go, you're using cosine of the angle and sine of the angle, but you have to use this angle in standard position, or the direction angle. Because remember, we related that to the unit circle. Okay? So that's 120 degrees. We also need to do the same thing with the wind. Okay? Now the wind, they didn't give us a separate picture for this, so I drew one for us, okay? This is the wind vector right here, this V2. All right? So this is V2. Now, it gave us a direction here of north 45 degrees east. That means this angle right here is 45 degrees. North 45 degrees east means we start at due north and we rotate towards the east 45 degrees. Okay? But again, that's not the direction angle for that vector. What would the direction angle be for this vector?
45.
Yeah, it would be rotating up here, and in this case it just happens to be 45 degrees. Okay? So, direction angle of 120 and direction angle of 45.
So now you just add them?
Well, no, those are what you want to use for your finding your unit vectors, okay? If you recall, our unit vectors are given by taking, if we want a unit vector, or if we want a particular vector with a certain magnitude in a certain direction, we use the magnitude that we want times the unit vector. And the unit vector we said was cosine of the angle, sine of the angle. And we took that straight from the unit circle. The points on the unit circle are cosine, sine. So the position vector for those points would be cosine, sine. Alright, now, why am I talking about finding component vectors? Well, that's because in the problem, they're asking for the resultant speed and direction. And anytime you see this word resultant, what should come to mind?
The adding two component vectors.
Adding vectors. Vector addition. Okay? That's where we have this equation here. V1, what the plane is trying to do, plus what the wind is doing, will equal this vector v. And vector v is what actually happens. Okay? So if you were looking from way up above, alright, you would see the plane pointing this direction, you would see or maybe feel the wind blowing this direction, and even though the plane was pointing this direction, its path would actually follow this red vector here, vector v, because the wind is impacting its path. Alright, it's kind of like swimming across a stream. If the stream is flowing, or the river is flowing, you might be trying to swim straight across, but your actual path is going to be like this, because you're going to float downstream as you swim across.
Why don't cars have that same path as the
It can a little bit, but the reason why it doesn't is because the road isn't actually moving.
Oh.
A plane is flying through a fluid substance, air. Whereas you have the friction of the tires on the ground that overcome that. That's why sometimes though, if you get a gust of wind, it can push you off course.
Or if it's
You can
raining.
feel-
Or if it, if it's
we're
raining,
talking
it
about
can't hurt.
planes. I thought we were talking about cars.
If it's raining, it can
Yes,
affect,
if it's raining.
it can make it easier for the wind to blow you off because it reduces the friction between the tires and the road.
You're waiting.
Question?
How do you know which one to use for theta, like the 120 or the 45?
Well, we're actually going to use both
And
because,
then you add them?
yes,
So you do cosine of 120 and then sine of 120? And
Yeah.
then okay.
we need to identify one more thing though first before we do this. But yes, we're going to write vector 1 and vector 2 both in component form so that we can then do the vector addition. Okay? That's where we're headed here. The last part though I need to identify though is the magnitude of both of those. Okay? The magnitude of V1, yes, they said it was going 500 miles per hour. Okay? So that's the magnitude of V1. What was the magnitude of V2, or wind?
70 miles per hour?
70 miles per hour. Okay? So, now we can get our two component vectors. Alright? Just going slow. There we go. Alright, so watch as I do the airplane and then I'm going to have you guys do the wind. Alright, so if I'm finding V1, I take the magnitude, which is 500, and I'm going to multiply that by the cosine of 120 degrees and the sine of 120 degrees, both of which you should know.
Negative 1/2.
Remember that.
I'm not looking.
Is it 24?
You're looking.
Cosine of 120, is that right? Negative 1/2?
Yes.
Yeah.
Yes. Okay.
And
We're
then
in the second quadrant, so
Three
cosine's
over
negative. Alright. And yes, sine of 120 is root 3 over 2. Okay. So, vector v is negative 250
Um,
and 250 root 3. Okay? What is 250 root 3?
like in decimal form?
Yeah.
7.
No.
Wait.
It's 250 times 1.7.
250 times root 3.
01 or 0?
0.01.
Yeah.
Okay, we'll do that. 0.01. Alright, so what is this saying about our airplane? Okay, our airplane is going at a bearing of 330 degrees, but what this says is even though it's traveling at 500 miles per hour, we are moving westward at a rate of 250 miles per hour. That's what the negative 250 means. And we're moving northward at a rate of 433 miles an hour. Okay? So even though we're traveling on an angle, okay, we're traveling 250 miles per hour west and 433 miles per hour north. That's what that's telling us for vector 1, the airplane. Alright, are there any questions about how we got that?
Where did we get the angle measures from? Did they give us that or did we find that?
They gave us the bearing, remember, 330, and we translated that into the 120
Okay.
as a direction angle. Okay?
And now we have to do the wind one.
Now you need to do the wind. So why don't you guys take a moment or two here and find
What did you just say?
what it would be for the wind. We said the magnitude's 70, the direction angle is 45. There's your formula. So go ahead and find what V2 would be.
Wait. Cosine. It's
Okay.
Well,
Did you get
for
this?
the wind, right?
Why are you using 500?
So you that's
Is it 99, 99?
We'll see.
Yes. You're right. No, not yet. No, I'm not gonna.
We're not talking anymore.
I hit one, but. Oh, me too.
Yeah, you don't have to draw on it.
I got it. It's
7.
49.
Yeah, 49.
It's
97.
Yeah.
What's the cosine of 45?
Root 2 over 2.
Good, root 2 over 2. And what's the sine of
Root
45?
2 over 2.
Goes over to.
Yeah, honestly, you win.
Alright,
Skill comes in.
so then when you multiply, what do you end up getting?
49.497.
0.497, so we'll make that 0.50. 49.50. Okay,
And the 70 miles per hour, that's just how fast the plane was driving.
that's how fast the wind was blowing, yes. Okay,
And then you add them together.
now we can add them together and we'll find what that vector v was. V equals v1 plus v2. So that would be 49.5 minus 250, so that's a negative 200.5. Okay? And then we have 49.5 plus 433.01, so that would be 482.51.
Did you just
Okay?
Sometimes math makes sense, and like it's not.
It does make sense. Okay?
It always makes sense.
Oh.
Not always. Always, otherwise it's not math.
They won.
You don't get it.
I'm having some issues here.
Alright, now, let's actually answer the question, because the question didn't ask for what's the resultant vector.
Oh.
The question asks for what is the resulting speed and direction.
Well, that's direction. Well, no, direction's like. Oh, oh.
How do we, let's think about this, what,
You get the direction of the speed, right?
We have the direction
Well,
is that.
we want the direction and the speed
482.5 over negative 200.5.
equals what?
That direction.
You're on the right track. For the direction,
It's just the unit
This is
vector.
slope, right?
hang on. That would be a slope. Yeah, 482.51 over negative 200.5. But how do we get the angle?
Tangent.
Tangent.
That equals our tangent of the angle. Okay? Tangent of the angle.
So you do the inverse tangent of that.
Yes, do the inverse tangent of that, and that gives us theta equal to what?
So we don't need to find the unit vector.
Inverse tangent.
Well, the unit vector was back here, the negative root 2 over 2, and
Negative
or
67.
Well, like, for
Wherever it
the
was.
result.
I got that too last week.
not for the result, no.
So direction means angle.
Direction means angle.
It's negative 67.4
Degrees. 4.
Okay, so we'll just make it 0.4. Now listen, is that the angle we're actually looking for here?
No.
No, it gave us that because if you remember, arctangent has a range from negative 90 to 90. So your calculator is always going to give you an answer between negative 90 and 90, or negative pi over 2 and pi over 2. However, what quadrant do we want our angle to be in?
Second.
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 Second, right?
I thought.
Second quadrant. And tangent is negative. Notice this is negative. So we know it would either give us a second or fourth quadrant. Okay? And because we were going in a northeasterly or northwesterly direction, that's second quadrant. So, what is theta actually?
360
It's 90 plus.
180 minus.
180 minus. Yeah.
Why is it 180 and not 360?
We want second quadrant, right? If we want second quadrant, that means that if this is this did tell us our reference angle was 67.4, but for second quadrant we subtract from 180, so theta is actually, good, 112.6. That is our direction. Okay? That is our direction. How would I find the magnitude?
Square root of negative 200.5 squared.
Let me move this out of the way for a sec. Okay,
You need more colors.
speed is the magnitude of v.
Right.
Alright, so that's square root of
200.5.
plus 482.51 squared. Take it down. Alright, and what do you guys get when you do that?
438. Yeah, I got 438.88.
You just said 5.
And that's miles per hour, okay?
I got 522.
522.
Well, let's see,
I got 522 also. Oh, never mind.
okay?
Yeah, me too.
That's why we, that's why we all do it, okay? Make sure that we're getting it right. So 522 point what?
5.
Alright,
Oh, yeah.
so here's a question, did the wind speed us up or slow us down?
You sped us
Sped us
up
up.
It sped us up.
22 miles
Now it is knocking us off course, but at least we're going faster, right?
to the wrong place.
Alright, so,
Are you Thomas?
No, it's Toma.
Oh.
Don't follow him on Instagram, guys.
anyways, So here we have our magnitude and direction, which gives us our speed, the resulting speed that we're going to go if our plane normally goes 500 and then the wind is blowing at that angle. Okay? Now, one question that was asked earlier was, what if they ask for a bearing instead of just the direction? And this is where you have to pay attention to what the problem asks you for. Okay? Here is the direction, 112.6. If they ask you for a bearing, depending on how they're giving their other directions in the problem, you could give a result like this. If that's 112.6, that means we went 22.6 degrees past north. So we could write that as north 22.6 degrees west. Alright? Again, this is only if they ask for a bearing. If they just ask for direction, this is the answer we're looking for right here. 112.6. However, we could also write a bearing as that angle from due north, okay, which is the more common one. So we would think, okay, well that's 22.6, so I need to go around 90, 180, 270, plus another 67.4, because that was a reference angle if you remember. That's a total of 337.4. All three of these give the same direction overall, but depending on what we're asked for, or what the context is, we might need to give a different answer. Yeah.
What's the difference between if they say like, will they always say like bearing something? They'll always say like bearing north or whatever. What's the difference between like giving a bearing and saying like due north?
Well, due north actually is a bearing.
Okay, so bearing.
Due north is just a bearing of 0.
So if they say like bearing south, then you do like.
That would be perfectly south, so that's a bearing of 180 degrees.
Okay.
You know, or if they say west, that's 270 degrees.
So it just means like the way it's going.
Yeah.
Why is it 270 plus 67.4?
This was a reference angle, right? 67.4. So to go from due north, we would have to go 90,
Oh,
180,
north, yeah.
270.
I was starting at the other.
Yeah.
Pilots use these all the time.
Yeah, pilots use this all the time.
Yeah.
337.4, so
They ask them
do,
what's your bearing and then they
yeah,
respond.
pilots use it all the time, so do people in ships.
Yeah. Ships too.
Yeah, so navigation uses bearings all the time. If you do stuff like orienteering, you guys know what that is? They're like given a map and you're given angles and stuff and you have to find stuff. Which is what the military does. If they're dropped in a certain location and they're told to go here, they've got to figure out what direction to go. Orienteering will sometimes use these directions here, the north, whatever degrees west, or stuff like that.
That's the compass mode. That's one of the
Yeah.
compass uses.
Yeah. So,
I got that.
When you report 337.4, you just put that, or do you put bearing north?
no, you would just say it's a bearing of 337.4. Alright, so I wanted to go over that example with you. It's a good example and it kind of shows you, how we can put different vectors together and then find out the result. Okay? This is why we need to recognize both vectors that are given as a magnitude and direction, but also recognize vectors that are given in component form. They're both significant. The component form allows us to, the magnitude and direction is maybe a little easier for us to understand initially, but the component form allows us to see how they interact with each other, easier, because it's easier to do the vector addition and whatnot, okay? Now, as you guys looked through some of the problems, what questions did you guys come up with?
I really just need like reinforcement on how to do it rather than
How to do like what?
like the magnitude times sine of x, cosine x. Sine of
Okay.
x.
So something like these.
Yeah.
Okay. Now this is asking for the component form of the sum. So this actually is just like the problem we just did. They just gave us the angles and magnitudes that we wanted.
It's so much easier this way. Even
Well-
though it's like the same thing.
Yeah. Things are just given out a little more explicitly. So here, let's go ahead and find vector u. To find vector u, we want the magnitude of u, which in this case is 5, times the cosine of 60 and the sine of 60. Alright? So again, we figure out what cosine of 60 is. That's a half.
We had 3 over 2.
Sine of 60 is root 3 over 2. So we now have,
Vector 5 halves.
2.5.
yeah, 2.5 or 5 halves,
4.3.
and 5 root 3 over 2,
It's 4.3.
4.3.
Yeah.
Okay. Alright, so there's vector u. Now I want you to think here. Don't miss the easy ones. If I have a direction of 90 degrees, that's going straight up, right?
Yeah.
So if my magnitude's 5, what is that vector?
0.5.
0, 5. 0, 5. You don't even need to use your formula. Because to go straight up 5 units means you're not going horizontal at all, you're going just vertically 5 units. Okay? So now it's saying what's the component form of the sum of u and v? Alright, u plus v is going to equal, let's be consistent here. It's going to be the 2.5, 4.3 plus 0.5. So we get, there we go. Okay? So again, we're just adding the component vectors. The challenge of these is actually finding what those component vectors are in the first place. Then it's just a matter of adding them together. Which isn't too bad. Okay. Alright, anything else?
How many other like sections were there?
2,
Just 2?
6, 4, and 6, 5.
Is our test gonna
Wait,
be
what?
on all
No, I meant like in this, like you know how like there's always groups of questions
Oh,
in each section?
well, we had some of these, which that was just like this,
Okay.
or the other one. You were just finding one component vector.
Oh.
Which again, by the way, number 67 should be a really easy one. If I have a magnitude of 3 and my angle is 0 degrees, then what is the vector? 3, 0. Okay? The others you would have to use the formula for. Okay?
If it's 45 degrees.
If it's 45 degrees, then all you really know is that your horizontal and vertical components should be the same in the end. Okay.
When we have our test, is it gonna be on all of chapter 6 or just from 6-3 on?
Well, it's gonna be 1 through 4. We're gonna look at 5 briefly, but I'm not gonna spend a ton of time, and it's not gonna be on the test for the chapter. So,
Will it be on the test for the following chapter?
no.
But that's our last assessment for this trimester, is that test?
Yeah.
Can you do the other one?
What's our test?
What, the Gulf one?
No, 85.
85, this one?
Yeah.
Alright, let's take a look at this one. I already have it worked out here, but we'll at least follow through with it. Let's set up the situation here before we look at the solution. Here we have a situation where we have this weight that's being supported by 2 separate pulleys, okay, and 2 separate cables. Now, anytime you're talking about a weight, that weight is going to pull which direction?
Down.
Straight down, okay? So basically, this vector here, it has what magnitude?
5,000.
5,000, okay? 5,000. Now, it says use the figure to determine the tension in each cable supporting the load. What is tension?
The pole, like basically how
It's
tall.
like a
Force.
Yeah, it's the force, it's the pull on that cable. Alright, so in other words, we want to find what the magnitude of this vector is and what the magnitude of this vector is. Okay? Those are the 2 magnitudes that we want to find. How much weight does that cable have to support?
5,000.
Alright? Well, actually, think about it. This is pulling straight down, so that's a right angle, correct? So let me ask you, if this is 5,000 pounds, all right, and this is a right triangle, is AC going to have to hold 5,000 pounds?
No.
No, what do it have to hold?
It'll like share.
More
Yeah,
than
more.
More than 5,000 pounds. Okay? More than 5,000 pounds, because that's a hypotenuse, right? And it, you can actually do this little experiment. Take a weight and tie something to it so that you can hold both ends of the rope, all right, and lift it up. And lift it up once with your hands right next to each other, okay? What you're doing there, that's like if these pulleys were both right in the middle, right at that point, okay? If that were the case, then they would only have to be able to support 5,000 pounds. And in fact, if you're lifting something like that, that will be the easiest, is if you have the 2 ropes together and you're pulling straight up. Alright? Then try to lift it after pulling your hands out to the sides like this. Try to lift the same object straight up. And the fact of the matter is it's harder. Why? Because of the angle. Because not only are you having to lift up, you're also having to resist the force that's pulling your arms together. Okay? I gave the illustration, and it's terrible artistry, but you'll get the picture. Okay? If you've ever watched the rings in the Olympics, the guys who do the rings are incredible. But you got the rings, and you got a guy, you know, he can hold himself up, you know. Here's his shoulders and his head, and
He's a mermaid.
he has feet. He has 2 separate legs. There you go. So, all right. So there he is. He's
Oh yeah, I got it.
there you go.
And then like this. It's
We'll give him feet. Yeah. He holds himself up. Those guys could probably hold themselves up like that all day. No problem. But one of the hardest moves on the rings. Do you guys know what it's called?
Like this, lift your feet up.
Yeah, it's like this. What's it called? The iron cross, yeah. And that's when they put their arms out wide, okay, and somehow they're able to actually hold their bodies up. Okay, here's his feet again. He has really small feet. Okay, and we'll give him
How tall is he?
pretty tall.
He's
evidently.
taller than me.
All right, so there you go. Now that is so much harder because not only is he having to hold his body up, but he's also having to hold his arms in so that it doesn't just pull his arms all the way out and then they go over his head. Okay, so he's having to use vectors in these directions, whereas here he's able to exert all his strength straight down. Okay, so it's much easier when they're closer together because he has to lift just his body weight instead of counteracting the other forces. It's the same idea here, and that's why the magnitude of AC and the magnitude of BC are going to be bigger. They're going to be greater than just 5,000 pounds. Okay, so if you have a cable and all it can hold is 5,000 pounds, you can't use it in this case because we need it to hold more than 5,000 pounds because of the angle. Alright, so let's think about how we would go about doing this. And this is where we're using lengths of things in combination with magnitudes of vectors. Alright, so what I did here is I divided this into two separate triangles. Okay? Two separate triangles. And you'll notice what I did here at the left triangle, I used the 10 inches and 24 inches to find this angle here.
It's so long.
Okay? How do I find this angle here, the 67.4?
The law.
You could, but you could.
97.4,
100.
and you can find that angle.
Well, we don't know the 67.4. How do we find the 67 before?
Long sign.
Tangent. Alright. Notice what we know. We know side angle side because of the right angle. So you could theoretically use the law of cosines to find the hypotenuse.
What did you do? Tangent.
But we don't want to use the law of sines or the law of cosines unless we have to.
Okay.
Alright?
Why?
Because they're harder than using right triangle trig. Tangent of A is opposite over adjacent, 24 over 10. Same thing over here, tangent of angle B would be 24 over 20. That's how we get the 67.4 degrees and over here the 50.2 degrees.
So you don't have
Okay.
to do the inverse tangent. You just do the tangent.
Well, yeah, we do, in order to actually figure
To
out what
find
A
A, you
is,
have to
we
do the
find,
inverse,
we
okay.
do the inverse tangent, yes. Now, the reason why I did that is because now we can start looking at the vectors instead of just the lengths of these sides. Okay? Now we're looking at the magnitudes of the vectors. We're trying to find the magnitude of AC. We know 5,000 pounds is the magnitude of this vector. So how could we find AC?
Oh, just use the Pythagorean.
We only have one side of it.
Why can't you just add them together? Because like that's your resultant vector now.
Wait, are you asking?
But here's the thing, guys. Listen. This is a length. We can't use that when we're talking about the
Oh,
vectors.
you're talking about the blue? Okay.
We're talking about the actual vectors here, the 5,000 pounds and the magnitude of AC.
Oh.
100.
Not tangent.
Cosine.
Sine.
Sine.
Sine of 67.4 would be 5,000 over magnitude of AC. Over here, what would we use to find magnitude of BC?
The sine of
Sine of 50.2. Okay? So, we're able to do that, then we can solve, and we see that this cable on the left side at 67.4 degrees has to be able to support a little over 5,400 pounds. And this cable on the right that's at 50.2 degrees, it's got to be able to support 6,500 pounds. Okay?
So you're saying, if that was real, I guess, if you're lifting a 5,000 pound weight and you use two different things to do it, it can still, each cable could still be holding more than 5,000 pounds? Well, why do we do that? What's the-
So if you're like weightlifting, you wanna put your hands as close together as possible?
I don't know.
No,
Well, you
no,
wanna
they
balance
don't
it.
No.
You want to be, well, here's the thing. It's a little different because you're holding a bar, and when you lift the bar, it's not going to be pulling your arms together
Okay,
like
yeah.
ropes will, because you have a stable grip.
I'll
But-
try.
But what you do want to do, for example, like when you bench press, you want to have your hands directly over your shoulders, shoulder width apart, so you're lifting straight up and down. You get guys who get a really wide grip, and they have to work a whole lot harder because they're using some of their grip, some of their strength to avoid bringing their hands together.
So if
They
those
have to
guys-
like push out and up instead of just straight up.
If those guys were right triangles, then like one arm would be bigger than the other arm.
Yeah, this is a guy whose one arm's a little longer than the other or something. But anyways,
That right triangle's a person.
you know, think about it. Try what at home. Try this, okay? Get something and hold it up in front of you, and then try spreading your arms apart.
Not if it's living.
Okay. And you'll feel the increase in strain because it's harder to hold that weight up the wider you get your arms apart. Okay, because it's pulling you in and you're having to hold it up. Okay? If you think about it, these two cables are somewhat pulling against each other, aren't they?
Yeah.
This one is trying to pull it that way, this one's trying to pull it to the right. They're pulling against each other. That's where the extra weight comes from. Okay? Now, we have this set up sometimes because if you have this on pulleys, then you can actually kind of move it back and forth. But anyways, you guys get the idea with the vectors. Okay? Alright, any other questions? Problems? Anything? Alright. So I know we've taken a lot of time going over these. If you did not work through these on your own, you need to do that. Okay? Don't just go based off of what we do in class. Okay? You've got to practice on your own, come with questions, and work things out. Okay? And on Thursday we're gonna pick up with section 4. Okay? We'll do that all on Thursday, Friday, Monday. And then our chapter test, it's only over the 4 sections. It'll be on Fusion Day. So for you guys Thursday.